So what we're getting into are exponents, and you'll sometimes hear these referred to as powers. And what do you get? Say you have something like this. Here, I'm going to switch my pins here. Excuse me. So these have two parts. You have a base, and then you have what's called the power, or the exponent. So you have your base, and then you have the power or the exponent. Now, what this means in what we're looking at is what's called repeated multiplication. So the idea is going to be this. Two with an exponent of 4 is 2 times 2 times 2 times 2. And if you multiply 4 2's together, you're going to get 16. This is going to be the case with anything you're working with as far as exponents go on any number. So for example, if you have 2/3 with an exponent or a power of 4, you're going to take 4 of these 2/3 and multiply those together. You're going to multiply all the numerators together. And you're going to multiply all the denominators together. And this will come out to 16 over 81. Yeah, you're not limited to fractions either. You could do this with decimals. So if we take 2.06 or 2 6/100 and we give it a power of 3, we have 2 6/100 times 2 6/100 times 2 6/100. If you multiply those together, wow. We're going to get that. So any questions about that? So whole numbers, fractions, decimals, we're just going to do the same thing. This tells us how many of these we're going to multiply together. Now, negative numbers, it's going to be the same thing. So we have -2 with a power or an exponent of 3. And we have -2 times -2 times -2. And we could follow order of operations. -2 times -2. Well, negative and a negative, when the signs are the same, you're going to get a positive. So this will be 4 times -2. And now the signs are different. When the signs are different, that's going to give you a negative answer. So this one we're going to kind of keep in mind off to the side. -2, the exponent is an odd number, and it gave us a negative answer. So any questions about that? All right. Now let's take -2 and give it an even exponent. Let's give it a 4. So -2 times -2 times -2 times -2. So these right here, again, negative times negative, the signs are the same, so that means you get a positive. They have a positive and a negative. Signs are different, you'll get a negative. Oh, I'm sorry. Whew. +4. Ooh, my bad. Ooh. There we go. Positive number, negative number. Signs are different. You're going to get -8. And then -8 times -2. Well, now the signs are the same again. We get +16. So questions about that? Now I mentioned you want to keep that -2 with an exponent of 3 off to the side, and this is why we're going to do this. So this is a little trick with negative numbers. So negative numbers and exponents. If you have an even exponent, so a negative number, like -2 with an exponent of 4, you get a positive answer. But if you take that negative number, give it an odd exponent, you're going to get a negative answer. So that's what we just saw. So if you take -2 to the 4, we got +16. But then if we take -2 to the 3, we got -8. So any questions about that? All right. So there's another thing with exponents and negatives you got to be careful of. And what it is, you notice that I've got parentheses on the negative numbers. If you don't have those, you're going to have some issues. You could have some issues. So let me show you how this can go. Let's say we have so this is where parentheses with negative numbers matter. So for example, if you take -3, you give it a power of 2, that's -3 times -3. And at the same sign, so you're going to get a positive answer, you're going to get 9. But if you see something like this, and this is a trick one that will come up from time to time. If you see something like this, what this technically means is -1 times 3 squared. Now we're going to get into PEMDAS. We've done a little PEMDAS already, but we're going to get back into it, this time working with exponents and roots. And the thing that we're going to run into with PEMDAS is we do exponents first, then we do multiplication. So this becomes -1 times 3 times 3. And I'm just going to cut to the chase. This will become, or we do the exponent first. Apologize. This will be -1 times 9, -9. So with parentheses, you've got the -3 times the -3. Without parentheses, this is -1 times 3 with an exponent. So you could get different answers. Questions about that? All right. Now, there's some special terms that go with exponents, and you'll see these from time to time. If there's an exponent of 2, we often refer to that as squared. And where that actually comes from, like let's say you're trying to find the area of something. And let's say it's 10 feet. And you have 10 feet. We'll just use units. I'll keep we'll just use numbers. So if you want to find the area of this square, well, the area is the side. They say side squared, but you say it's length times width, or 10 times 10, or 10 exponent 2. And so this is kind of the idea where the square comes from, that the 2 refers to the idea of finding the area of a square. So you'll see that from time to time. Now, what you'll also get, though, is when you have a 3. And if I'm going too fast, let me know. So let's say we have the next one, an exponent of 3 is cubed. So like 2 cubed means 2 with an exponent of 3. Now where this tends to come from is if you're trying to find the volume of a cube. And it has, say, a length, a width, and a height of 10 units. So the volume is length times width times height, or 10 times 10 times 10, or 10 with an exponent of 3. And we would call this 10 cubed. The other one, we would call it 10 squared. But we would call this 10 cubed, and the example before would be 10 squared. But you'll hear those two terms used from time to time. So any questions about that? Now, another use you'll see exponents in is in scientific notation. And you might have seen this before, like 3.12 times 10 to the, say, the 8th. What this just means is 3.12 times 10 eighths. Oh, I'm sorry, 8 tens, 8 tens. And the way you can do this, each time you multiply by 10, you're tacking on a 0 to this number, or you're moving the decimal one spot to the right. So what this turns out to be is this number. And again, the reason this comes up is that each times 10 moves the decimal one space right. So any questions about that? So some special properties with decimal or exponents. A number with 1 as an exponent results in just that number. So what it means is this. If we give 5 an exponent of 1, this is just equal to 5. Give 0 exponent of 1, that's just equal to 0. -7 exponent of 1, just -7. 4.17 exponent of 1, and just 4.17. 9 1/2 with an exponent of 1, 9 1/2. So giving something an exponent of 1 doesn't change it. It's actually a math trick that you can assume every number you encounter actually has an exponent of 1, like an invisible exponent of 1. Sort of like there's an invisible 1 underneath every whole number, or really underneath every number. And you can use that for fraction multiplication. But any questions about that? Now, another property you get with exponents, and this is a peculiar one, I have to be kind of careful with it. It has to do with 0. So any, and here's the key thing, non-zero number with an exponent of 1, I'm sorry, 0, gives you one. That's kind of unusual, I'll admit. But that's what it is. Any non-zero number with an exponent of 0 gives you 1. So 5 to the 0 is 1. -7 to the 0, well, that's just going to be 1. Our 9 1/2 to the 0 is 1. 4.19 to the 0 is 1. Now, we mentioned it's got to be the base, the number that receives the exponent or the power. That has to be non-zero. And so what happens if you try to give a base of 0 an exponent of 0? Well, it's going to be this. 0 with an exponent of 0, we say that's undefined. That one we don't try to mess around with. We leave that one be. So any questions about that? Now, the last one I'm going to mention, it's not really in your book. I'm just going to sort of mention it because you'll run into it. So to just kind of round off your experience with exponents, I'm going to mention negative exponents. And they have a very particular meaning. So this is a little bit kind of an extra thing. But you're going to run into this, especially with scientific notation. What this means is flip everything. Well, I want to be careful saying everything. I'm just going to say flip. So what it says is this. If you have 5 to the -2, I'm going to say flip to lose negative exponent. So we try to write exponents without the negative, but we have to follow a certain rule that gives us permission to get rid of the negative, and it's flip. So we write this like that. Or if you see something already flipped, like let's say 4 exponent of -3, well, you flip it again to make the negative go away. And so this, if we continue, this will be 1 over 5 times 5 is 25. And this one, if we keep going, and these are both separate examples, this will be 64. But that's something you do with negative exponents, you flip. So how does this affect scientific notation? Because you'll see this with scientific notation. So let's say we have 4.2 times 10 to the -9. It's like, what do you do with that? Well, we're going to flip. So this time, we're just flipping the part that's the base and the exponent. That's the only thing that flips. So this becomes 1 over 10 to the 9. Or you can call this 4.2, and there's that invisible 1 times 1 over a billion. So you multiply across, we get 4.2 over 1 billion. And then you could punch that into your calculator, or when you divide by a number that's a 1 with a bunch of zeros, it just says move your decimal point to the left by the number of zeros. But here, I'll just crank it through the calculator real quick here. And sort of the moral of the story with this, when you see scientific notation using these negative exponents, you're dealing with very tiny numbers. And the reason people use scientific notation, they would rather write this than write all these zeros. And especially if you're dealing with like anything involving like atomic level type work, you're going to be dealing with a whole bunch of numbers like this, or something on this scale. This isn't an atomic scale, but it's pretty darn small. You're going to get a whole bunch of these numbers. A lot of people just like to write it like this. Also, it's a little easier to deal with. And let me see, did I miss a zero? Got 9 zeros. Let me double check this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, no, we're good. Again, it's easy to miss a zero. It's much simpler to maybe do that, depending on who you're talking to. So that's the idea of exponents. Any questions about that? And that's a little bit of an extra thing, but it's out there, and that's what it means. Now, next up are roots. This is the same section. And the way roots work are this. We're going to talk about square roots. Now, we mentioned the term square means a number times a number. So this is how a square root works. Because 5 times 5 is 25, then the square root of 25 is 5. So that's the whole idea. So because 5 times 5, a number times itself gives you 25, then the square root of 25 is that number. So you can think of this in terms of our square again. We're finding the area of a square. So this is the square, and then these will be the roots. So any questions about that? So to a large extent, what's going to happen is, in the beginning at least, square roots are going to be kind of a test of really your multiplication tables. So another example. One half times 1/2 equals 1/4. Then the square root of 1/4 is 1/2. Now this becomes a little tedious, I'll admit. You have to write this all the time. So what we often do is we symbolize a square root with this symbol. Now it's kind of a peculiar symbol. Like, why do we use that symbol to represent square roots? The symbol, there's a lot of different explanations as to where the symbol comes from. One of them is it comes from an Arabic letter, and this isn't on the test, but there's an Arabic letter that I think is shaped like this. It might be the j sound, and it's used for the word root in Arabic. And then when that word came to Europe, or it might have gone through Spain first in Spanish. Well, it's Europe. Spain's part of Europe. This was eventually adapted over time to this. So there's a lot of mystery, though. There's all kinds of stories of where that might have come from. It might have come from the Latin R, which is the R that we use, the lowercase r for root, where someone did this, and then over years they adapted it into that. So that's where two possible sources of where this symbol comes from. But the way we use it, instead of having to write all of this up here, we can do this. 1/2 times 1/2 is 1/4. Then the square root of 1/4, we put the number underneath the symbol, is 1/2. And in math, we're always looking for ways to do things more efficiently, a lot quickly, or quicker if we can do it. So any questions about that? So we'll do a few of these. So since 9 times 9 is 81, then the square root of 81 is 9. So let me break out my calculator here. Let's play around with this a bit. Let's say we have 0.24 times 0.24. What does that give us? 0.0576, or 576 10,000ths. So since 0.24, or 24 hundredths, times 24 hundredths gives you 576 thousandths, then the square root 576 thousandths equals 24 hundredths. So any questions about that? So that's all that square roots are. That's it. So to know the square root using this technique, you got to know which two numbers, what number was multiplied to itself to get you that number. So for example, let's say we have this. Find the square root of 16. And we might recall, since 4 times 4 is 16, well, once again, that must mean the square root of 16 is 4. Now, there is a little warning I'm going to put here. There's something I'm sort of deliberately leaving out. And it has to do with negative numbers. And I'll explain why. So here, let me make a note. So 4 times 4 is 16. So this means the square root of 16 is 4. But this is also true. Negative 4 times negative 4 gives you 16. So then the square root of 16 equals negative 4. So which one's correct? This is a number times itself. Now I gotta warn you, if you have a positive and a negative number, those are two different numbers. You can't take a square root. All right, technically you can, but you end up getting what's called a two-dimensional number or a complex number. That's for another time. But it's a number times itself, number times itself. So that means you have a squaring going on here. So as long as it's a number times itself, it's legit. So how do we know if someone says, find the square root of 16, which answer should we give? So which one should we give if we're asked to compute the square root of 16? Well, there's a little notation answer here. We basically have two choices. We have a positive or a negative answer for square root of 16. And typically the way it works is this. If you just seen a plain square root, they want the positive answer. But if you see a minus in front of the 16, they want a negative answer. you'll often see it like that. They'll break it up like that, plus or minus. So that does come up with square roots. And I'm looking at the homework section for this chapter, section 6.4, and it looks like they all want positive square roots. You're going to see something like that. So any questions about that? So the last thing to mention, and it has to do with a special situation like this. And these are going to be irrational square roots. So if you take the square root of 3, now this is something you're going to want to do in a calculator. I'm going to do this right now. So let's find square root 3. And I get this long number. You might not always know what you're seeing an irrational number, but that's what we have here. What it says, if I take the square root of 3, I'm going to get a number that has actually infinitely many digits. These are the ones my calculator happens to show, but they're going to keep going on forever and ever. And what we mean by an irrational, the decimals go on forever, but unlike other numbers we've seen where the decimals go on forever, like 1/3 or 2/3, you can't represent this as a fraction. So this is actually a very special kind of number. If you've worked with the number pi, 3.14159, it goes on forever and ever. It's also an irrational number. You approximate it. You'll see people approximate pi with like 22/7, but that's an approximation. It's not actually the full value of pi. So these numbers are kind of tricky, but they do come up with square roots. So what it says is this: what do we do with these kinds of numbers? We do two things with them. One is we might round them off. So if you try to come up with the square root of a number and you can't come up with the square root in your head, so you might put it in a calculator. You might get something like this. And so what you might do is round it off, say, to the thousandths place. Oh, let's go to the hundreds. So we rounded this to the hundreds. The other thing you might do is leave square root in symbolic form. And so instead of trying to come up with a number, we just might leave it like that and say good enough. If we can't come up with a square root that's like square root of 25 is 5, square root of 16 is 4. Instead, we're going to get an irrational number. We'll just leave it like that. And one of the advantages to leaving it like this is it lets somebody else in the future decide if they want to round it off or not. So where we rounded off here to the hundredths, a future person might round this off to say the 100,000ths. They might do something like that instead. So this kind of tells them to break out their calculator, pull up that entire number, and then it's up to them to decide how they want to round this off. So any questions about that? And again, how do you know you have an irrational square root? Well, you don't necessarily. What you can do is you try to come up with, say, what's the square root of 4 or something like that. And it's like, well, okay, I think I can do the square root of 4. 2 times 2 is 4. So square root of 4 must be 2. But then you might run into something like the square root of 5, and he's like, I can't think of a number times itself that gives 5. I can't think of that at all. And so you say, I better check this one on the calculator. And you check it on the calculator, and sure enough, you're going to get an irrational number. And so you got to decide, do you round off your answer, or do you leave it in symbolic form? So there's some different things there. All right. So the last thing to mention, it's to return to PEMDAS. I said, now we're going to update PEMDAS to include exponents and roots. And this is the last thing before we get into algebra. Because when we do algebra, we're basically going to go through PEMDAS except backwards. All right. Just looking at the homework problems, trying to think of some good ones here. This might work. So the only thing I'm going to mention, though, is that the insides of square roots, these act like parentheses. Or the inside is treated like it's in parentheses. So that's one of the tricks with this you want to kind of keep an eye out for, and that can be a little tricky. Now the thing to mention, though, is that with multiply and divide, these are actually treated to be equals, and we always do those left to right. And the same with adding and subtracting, we do those left to right. So any questions before we do some examples? All right. So let's say we have something like this. Now, according to PEMDAS, we do parentheses first, and then we do exponents and roots, and then we multiply, divide, then we add and subtract. Well, for this one, we can treat the root as if it's parentheses. So you can think of it sort of like this. And you might be wondering this 3 next to the root. I'm going to fill in some of the invisible things. When you see something in front of a square root like that, that means multiply. This is one of these shortcuts in math that can be kind of irritating. When you see something next to a root, there's an invisible multiplication sign. And so you can think of parentheses being here. And you've got that. So let's work in the parentheses first. Now, inside the parentheses, we have to subtract or do an exponent. And the exponents are first. Now, this is 5.2 squared minus 3. I'll put that times. And then we have 52 minus 25. Now 52 minus 25 is 27. Now let me check one thing, because there's an issue that's going to come up here. And let me just make sure that I'm on the same page with the author on this. So what I'm going to recommend is going to be this. Use as many decimal places here as your calculator allows. Now, this is a number that does not have what's called a perfect square root. So that means you might have to drag a bunch of decimals with you for a while. So the next step we're going to do is well, we'll get to that in just a second. But now we've taken care of what's inside the square root. Now we're ready to take the square root of this number. It's not a perfect square root. So, okay, that's not going to be a problem. But now let's take a look at everything again. We've taken care of those inner parentheses. We don't have any more parentheses, so we're done with those. But we do have an exponent and a root. And we also deal with these going left to right. So this is on the left. We'll calculate that one first. If you go 5.2 times 5.2, 2704. So this is what I'm going to say is when you take the square root of this number, the answer here, they want rounded to 2 decimal places. I'm going to round at the very end. I'm not going to round in the middle of the calculation. I'm going to round at the very end. So it means I'm going to carry with me possibly quite a few decimal places for the rest of this problem, but that's going to give you a better answer. So this is one of these irrational square roots. So we're going to take the numbers the calculator gives us. And now we've got to choose between subtraction and multiplication. And multiplication is first. And again, that's following PEMDAS. So again, we're just going to get a bunch of decimal spaces or decimal places, and we'll just carry those with us. And lastly, we're going to subtract. And that'll give us 11. And rounding to the second decimal place, we're going to 11 and 45 hundredths. So questions about that? I'm going to double check this. Let me double check this. But that's what I know from my other courses. When we do these kinds of calculations, we'll have you carry the decimal numbers all the way through to the very end. So let me do one more example. Let's say we have this. Now again with this, when you've got something in front of a square root, there's an invisible multiplication sign. You could use an X or a dot. I'm using a dot, but it's the same thing as the X. And when you have these large complex fractions, I remember the term there, this is just a giant division sign. And the best way to handle these is we'll save the division for last. And you can think of the top and bottom as having parentheses of their own. So the bottom's pretty easy to do. As far as the parentheses go, it's 6. Now this one, we have a choice between taking a root, computing an exponent, or multiplying. Well, according to PEMDAS, exponents and roots are first. Multiplication will be second. And we compute the exponent or root on the left first. Again, we're going left to right. So 3 times 3 is 9 times square root of 24. Now square root of 24, so let's see, 4 times 4 is 16, so the square root of 16 is 4. 5 times 5 is 25, the square root of 25 is going to be 5. 24 is between, so you can kind of figure out, how do I know if I don't have a perfect square for 24? Well, 4 times 4 is 16, so that means the square root of 16, and we're only interested in the positive square root. It's going to be 4. And then if we take 5 times 5, which is 25, the square root of 25 is 5. So 24 is somewhere in the middle here. So this means the square root of 24 is going to be between 4 and 5. Oh gosh, I can't think of a number between 4 and 5 that multiply to itself gives you square root of 24. Break out the calculator. Square root of 24 is, ooh, that looks like an irrational number. So we'll go with that as an irrational number. So now we have 9 times 4.898979486 over 6. This is a multiplication. And so now we're going to multiply the 9 and that irrational number. If we do that, we get 44.09081537 over 6. And now at the very end, we're at that large division sign. Now we divide. Save the division for last. We get 7.348469228, or approximately 7.35. And that's going to be our answer. So any questions about that? So that's it for exponents and square roots. That's the last of the pre-algebra type things that we're going to be looking at. We're going to jump into chapter 7 next week. Not next week, I'm sorry, this Thursday. And what's going to happen there, we're going to need to do a test. We do need to do another test. What we will do is I'll put together a kind of study guide, like a pre-test, which basically what it is, it's just going to ask you everything. Pretty much any type of question I'd ever want on a test is usually on the pre-test, but it can kind of help sort of, I guess, sort of put right in front of you what you need to study. It's kind of a study guide is what it is. And then we'll get into algebra on Thursday. We'll do that. So any questions, let me know. Other than that, oh yeah, and we're going to keep working on the grades. Try to make sure Pearson's displaying all the work that's you've done so far as your grade, and try to get that sorted out. So that's it. If you have any questions, let me know. Other than that, have a wonderful evening.